Good morning. Let's see, I almost forgot to start this on time today. Let's see, I've already got some example problems posted that I'm going to be doing today. And those of you watching this not live may want to print those things off and try them out. I'm just going to kind of barge through those problems today. And those of you watching live, if you have any questions, feel free to ask at any time. Let's see, later this afternoon, I should be able to get your first homework assignment posted up there. I've actually got it kind of, all the problems on it selected already, so I should just have to post it. And that'll be on the sapling for this class. I'm using a different homework system for my astronomy class, so I need to keep them straight. Okay, something I wanted to show you, and I'll change the screen here, and that is, where did I put it? Screen 2, I guess, worked good enough. This is the formula sheet, which I've got included in today's handout, so you could print one off if you want. And I have it in both Word form and a PDF form. Sometimes the version in Microsoft Word will look weird depending on which version of Microsoft Word you happen to have. So if it does look weird, just go ahead and open the PDF. You can actually open a PDF with Microsoft Word, so you may not be able to edit it, but you don't want to edit this anyway. You want to just leave these formulas alone. And this probably looks pretty intimidating, but it's the bunch that we'll use for the entire quarter. So don't worry about that too much. Today, pretty much the only equation we're going to be using is this one up here in the top left-hand part that's looking at average velocity. We may introduce a second equation in here today, but mostly we'll just be working with that average velocity formula. And when we have tests, you can print this off and use it for the test. Numbers that you might need on the test, like the acceleration due to gravity, I usually have it on there in a little table at the start of the test, so you'd have it available as well. And that's about all I can think about to tell you about that at this point. As we go through the quarter, you'll become familiar with more. And oh, I've got the acceleration due to gravity on this anyway. It's in this box right here. So you don't have to know that number either. I think your book tends to use 9.80 meters per second squared for the acceleration due to gravity. Turns out in Moses Lake, it's closer to 9.81 meters per second squared. So that's a value that I tend to use, but it isn't going to make any difference on the problems we do. We're not going to, if you're within, let's see, what is that, 1 part in 980 on your answer, I call that right. So we're just not going to worry about that. Anyway, that's the equation that we'll be using today. And I think I'm going to hop down to, let's see, this thing, and be working there for the rest of today. Okay, you should be seeing something with a pin on it right now, I hope. Piece of white paper. And I want to introduce that formula for average velocity that we had on there. In an algebra course, you would have used a distance equals rate times time equation probably. And if you solve that for the rate, you get the distance divided by the time. Well, we're going to be a little more sophisticated than that. Instead of talking about distance, we'll talk about displacement. And when we talk about displacement, we're going to use x2 minus x1, or sometimes it'll be x final minus x initial. But at any rate, either one of those, we're going to call it delta x. And so we'll be using something like that. And then instead of a single time, we might talk about time difference. It will often be T2 minus T1 or T final minus T initial, or if T initial happens to be 0, it might just be T. So sometimes we'll use that. But at any rate, that V average, and this turns out this formula is good whether you have acceleration, constant acceleration, or no acceleration, but the average velocity, which sometimes is just written with a bar over it, and on your formula sheet, I wrote it with just a bar over it. So yeah, that's the way it looks. But anyway, it ends up being x2 minus x1 over t2 minus t1. The x2 minus x1 is the displacement. The magnitude of it would be the distance traveled, and then t2 minus t1 is just how long it took to go somewhere. So an example of using this might be, let's see, an object travels from x equals 3.0 meters to x equals 8.7 meters in, I don't know, 4.2 seconds. What is its average velocity? Okay. So that would be a really simple question. Well, in this case, we can say that x2 is equal to 8.7 meters. Let's call that 8.7. So x2 equals 8.7 meters. x1, let's just call that the 3.0 meters. So, and then let's see, about those times, we could let the time that it was at the 3.0 meters be 0. All we know in this case is actually the difference in times between the two. So we could just say T2 minus T1 in this case is 4.2 seconds. So let's just say that. Sometimes we can let that initial time be 0 if we want to. And so we'll do that a lot. But in this case, it's only the time difference that we need. So we can just calculate the average velocity and say x2 minus x1, 8.7 meters minus 3.0 meters divided by the delta t, 4.2 seconds. Now, something to notice here, I'm writing down the units with those numbers every time I do it. And that's what I expect to see on homework and tests too, by the way. So we'll keep going with that. Let's see, I can do that in my head. Looks like 5.7 meters to me. And then that's a calculator problem. How many significant figures can I keep in my result? Okay, looks to me like 1.4 meters per second. And I can only keep 2 significant figures because that's how many I've got in my least accurate number here. So 1.4. Notice that's 1 decimal place, but it's 2 significant figures. And I've got a quiz on significant figures that's online or on the Canvas site, and I'm going to give you 3 chances to take it, and the only score that counts will be a perfect score on that thing. So you should probably, well, you can try it once and see how you do on it if you think you know significant figures real well. And if you don't do well, then I would advise watching all of the videos on significant figures carefully and then retaking it. So, okay, so anyway, there's an average velocity thing. A question that might accompany this, if the velocity remains constant, where will the object be let's see, let's just say 10.0 seconds. No, I don't want to do 10.0. People would try to do it in their head. Let's say 8.5 seconds. Whoops, don't need seconds twice. After passing the 8.7 meter mark. So what can we do?
A question about your Canvas.
Uh-huh.
So I don't see like worksheets. I go to modules and it has the assorted useful files, but I don't see anything. Okay. But like I don't see grades.
There aren't any grades. I don't put grades on Canvas. So I let you keep track of grades, and so you can keep track of them, but I don't stick that stuff on Canvas. I don't like the Canvas grading limitations, and so I just don't use it. But let me show you the modules. If I switch over to that here, let's see, new screen share, go back to screen 2, I think. Yeah, that's what it is. This is the modules for our class. And week 1, day 1, all I put on there was, I just made up the problems I was doing that day, so I didn't have anything on there. And it was mainly talking about accessing the textbook and signing up for the homework on that day 1 thing. And then day 2, I think all I've got on there is just the video. Again, I was just doing things live. But today, if you go to there, there's a student handout for today that you can print off. And then there's the formula sheet as well. And then after class today, once I get the video processed and uploaded to YouTube, then I can put a link to it here. So that's all there'll be on there. And from the student view here, all you've got Office 365, which I guess you can use that there. I don't know. I'm not sure just how that works. E-learning videos, if you're not familiar with Canvas, you can do those. And otherwise, it's just announcements and modules and home. So I don't put grades up there, which is why I pulled them out of there. You should be keeping track of how many homework assignments there are, how many points there are on each one. Same with labs. And also what your scores on them are. You can make yourself a little sheet for that and kind of keep track of how you're doing on that. And when you have a test, you can keep track of doing on that. And estimate your own grade, because it's basically arithmetic for doing that. So that's how you would assign that. Something I really dislike about the Canvas grading scheme is that, let's see, if I haven't graded an assignment, it gives you the impression that you have 100% on it, and whether you did it or not. And that's just not true. You don't start with a grade of 100% on something. You start with a grade of 0, and then you have to complete the assignment in order to get 100% and do it correctly. So anyway, I'll let you estimate your own grades and keep track of that stuff. And one of the reasons I do that is because I weight things differently at the end of the quarter, and I can't remember where I put the syllabus for this class. I'll be sticking that up here soon. One of the modules will actually be the syllabus for the class, but I don't have it up there yet. So anyway, that's why I do that. Oh, where was I? I was solving a problem. Now I forgot what I was doing. Oh, we still have to figure out where that thing's going to be after a while, is what we have. So let's see how we can do with the where that thing is going to be. Now, this is an example of taking this equation and turning it into something else. And I'm actually going to be after kind of an x3 in this equation. I'll have the same average velocity that I got in the other one, 1.4 meters per second. But this time, it's going to be some x final, I guess. The initial thing is going to be the 8.7 meters mark. And the time that it's going to take to get past this thing is going to be 8.5 seconds now. Okay, it's got the same average velocity. I know where it's starting from, and I know how long it's traveling for past that point, but I don't know what the final thing happens to be. And so I'll write it like this, and then solve that. And then I'll show you a way that we'll get another equation out of this equation, or out of this one, that we can sometimes use. So if I multiply out from underneath by 8.5 seconds, I'll have 1.4 meters per second times 8.5 seconds is going to equal my final position minus 8.7 meters. And then I just have to multiply stuff out and add it together. Multiplying on the left side, 8.5 times 1.4. I get, let's see, 12 meters. And that's as well as I can do with significant figures, and that'll be my x final minus 8.7 meters. Add that onto there. When I add 8.7 to 12, I would get 20.7, but I can only keep two significant figures, and so I would call that 21 meters when I'm done, and that's where it'll be. Now, this was a little bit complicated to work through that way. Let me show you something I can do with this equation to get something a little more reasonable out of it. And what I'm going to do, instead of calling it x2, I'll just call it x. And instead of calling it x1, I'm going to call it x0, x sub 0. And I'm going to let t sub 1 is going to be 0 seconds. And then when that's the case, x1 becomes what we call x0 is the way we pronounce that, as in N-A-U-G-H-T. That's kind of a British terminology. But what that means, whenever there's a subscript of 0 on something, it means it's the position when the time is equal to 0. And when that's the case, that average velocity equation looks like this. It becomes just x minus x naught divided by, well, the second time I'm just, instead of t2, I'm going to let it just be t. And then if I multiply out from underneath by that, I get v average times t equals x minus x sub 0, or x minus x naught, or x is equal to x naught plus v average times t. And this is an equation that gives us position as a function of time. And so it's a position versus time equation. And all we have to know for it is where it starts from, where it is at time 0, and where it ends up. And I think it should be, let's see, one of the equations that I've got on here. Oh, it is. Yeah, it's in a constant acceleration equation. Turns out this equation works when you have constant acceleration, but you do have to use the average velocity in that case. So the v average there. I sort of prefer the for v average to write it with a little subscript, although it's kind of a long subscript. But your book uses a bar on top of it, and looks like I used a different formula to get this v bar than I used for that v bar, and I may have to fix those. But at any rate, this will be another useful equation. And this works if you have 0 acceleration or if you have a constant acceleration. That equation will work. And here's how I could have used it in this case. I could have said, if the velocity remains constant, where will the object be 8.5 seconds after passing the 8.7 meter mark? Well, let's just start the clock then. And we'll say x naught is equal to 8.7 meters. So then I just say, okay, x naught is 8.7 meters. V bar, the average velocity, is at 1.4 meters per second. And the t that we're interested in here is 8.5 seconds. And so then where it's going to end up is where it started from, plus v bar, 1.4 meters per second, times 8.5 seconds. And so there, that's not a bad calculation. And when I do it, just 8.7 plus 1.4 times 8.5, and I get 20.6, but I can only keep 2 sig figs, so 2 sig figs on that. Just call it 21 meters. So there. And familiarize yourself with that equation. Again, it's on the sheet here. Here's our definition of v average, but then we can use that in there as well. So that's a constant acceleration equation. Okay, I want to dive into this other thing here. This is the worksheet that I have for today. And I'm just going to plow through here. You may try printing this off and redoing what I'm doing here later, but the following data table shows the position as a function of time for an object. So x would be the position, t is the function of time. And I have you graph the position as a function of time for the object. Now, here's the thing about graphing. Whenever you're making a graph, the thing that comes before as a function of goes on the vertical axis, and the thing that goes after as a function of goes on the horizontal axis. So this is going to be different. We're going to have time on the horizontal axis. That's the thing it's a function of. And we're going to measure the time in seconds. And so whenever I make graphs, I label the axis with the quantity it represents, in this case time, and the units for that. So that's what I'll have. And on the vertical axis here, I'll have x. And so I'll have x measured in meters on there. Now for the time, it goes from 0 to 10. Well, this is 5, 0, 5, 10. That looks good to me. On the vertical axis, I have to somehow get all the way up to 45. But let's see, what if I had 0, 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. That'll work. Okay, so I just figured out the dimensions for my two axes, and I've got what I need on a graph. I've got labeled axes with units, so they each have units, and I try not to call this horizontal axis the x-axis because it's not. It's the t-axis here. And I tend to not call this axis the y-axis because it's not. It's the x-axis. But this is a horizontal axis and that's a vertical axis. So it's better to think of it that way. I think we do you a disservice in math classes where the horizontal axis is always the x-axis and the vertical axis is always the y-axis. And then as soon as you get outside of a math class, every graph you see is something different. It might be stock prices versus time or something like that. Could be anything, but it's not just y's and x's, it's real things. So we should stop thinking of them that way. This will become more apparent when we do labs and I have you graph data for those. But here we go, graph the position as a function of time. All right, at 0, it's at 5 meters, so that's where it starts. 1 second, it's at 9, so this is 10, so it's a little bit short of that. 2 seconds, it's 13, there's 10, 13 is going to be about there. I'm just estimating on here, I'm not trying to be too fancy. At 4, it's 21, which is, wait a sec. Oh, at 2, it was that. 3, it's 17. 5, 10, 15, 17, and then 21, and then 25, and then 29, 33. This is kind of a predictable graph. At 8, it's 37. At 9, it's 41. And at 10, it's 45. Okay, so there's my graph. And I just have dots because that's the way it is. So there's part A. Determine the average velocity for the interval from 0 seconds to 5 seconds. Well, the way you would do that is this. V average is going to equal the position at 5 seconds minus the position at 0 seconds divided by 5 seconds minus 0 seconds. Okay, well, where is it at 5 seconds? It's at 25. So 25 meters minus at 0 seconds, it's at 5 meters. And the bottom is just going to be 5. I can do this in my head. 25 minus 5 is 20, divided by 5 is 4. So I get an average velocity of 4 meters per second. Then it says determine the average velocity from 3 seconds to 10 seconds. Well, I do the same thing, except I replace this with 10 seconds and this with 3 seconds. So V average for that stretch will equal, let's see, x of 10 seconds minus x of 3 seconds divided by 10 seconds minus 3 seconds. So 45 meters minus at 3 seconds, it was at 17 meters. 10 seconds minus 3 seconds is 7 seconds. Let's see, 45 minus 17 is 28. So I'll have 28 meters divided by 7 seconds, which is 4 meters per second. So how do they compare? They look like they're the same to me. Could I tell by looking at the graph how the two velocities should compare? Well, yes, I could. Turns out on a position versus time graph, the slope is the velocity because average velocity is delta x over delta t. Delta x on here is the rise, delta t is the run, and the slope of a graph is rise over run. And this thing has the same slope. In fact, it's a straight line. And so at least for these 10 seconds, it's got a constant velocity. Now, this asks me to write an equation of motion for the object, and that's an equation of x as a function of t. It turns out that equation of motion will be the equation of this straight line. Now, you're probably familiar with straight lines that look like y equals mx plus b. Okay. M is the slope of the line. B is the y-intercept. Well, the slope of my graph, well, for one thing, it's not y versus x. It's going to be x versus t. So that's what I want. But it's still going to have a slope and a vertical intercept. And it'll be x equals the vertical intercept. We tend to stick the vertical intercept first. That's where it is at time 0. That's where it is, the vertical intercept. Well, that's 5 meters. Plus, m is the slope. That's my average velocity. That's 4 meters per second. There you have it. That's an equation of motion for this object, x as a function of t. Now, I could also write this as x equals x naught, or x sub 0, plus v average times t. Okay. Anytime you've got constant velocity or a situation where you have constant acceleration, you can use this equation. But this looks like that for this particular situation. So it's good to be able to go back and forth between looking at a graph for something and then pulling off an equation for it like that. Okay, let's try another one. This one may end up being a little weird. Ooh, looks like I had some bleed through of ink, but that's okay. So another following data table, position as a function of time for an object. And again, I've got t's and x's. I'm going to use the same scale I did last time. So on my horizontal axis, I'll have t in seconds. Position as a function of time. So I want to graph that. That means what goes after as a function of is on the horizontal axis. So time goes there. And the thing before as a function of goes on the vertical axis. By the way, that's just a custom that we use. And so you may not have ever heard that before, but it is the customary use of as a function of, or making graphs of that. So I'll have x in meters on the vertical axis again, and I can have 0 down here, 5, 10 for time, and I think I'll use the same thing I had before. Heck, I'm not supposed to get phone numbers when I'm working, or phone calls. Let's see, 0, 25, 50. So we've got that, except we're not going to need to go that far. Let's just graph it real quick. At time 0, we're at 5 again. And then we go to 9 again. This looks kind of familiar. And then 13 is about there. And then 17, which is about there. And then 21, which is about there. and 25. Oh, but then we go to 22 and 19 and 16 and 13, about there, and 10. Okay, and if you couldn't have done it that fast, don't worry about it. Maybe it'd take you a bit longer to do that. But anyway, that's the way it works. Determine the average velocity for the interval from 0 seconds to 5 seconds. Okay, that'll be, average velocity is going to be x of 5 seconds minus x of 0 seconds divided by 5 seconds minus 0 seconds. And I think the data is exactly the same as what I had for the last graph, but it'll be 25 meters minus 5 meters, that's where it was at 0, divided by 5 seconds, and I get 4 meters per second. That's no surprise. For the first 5 seconds, the data is identical to what I had on the first page, so that's okay. But then it says, determine the average velocity for the interval from 6 seconds to 10 seconds. Okay, let's see what we get. That'll be x of 10 seconds minus x of 6 seconds divided by 10 seconds minus 6 seconds. Well, the denominator is 4 seconds. I can figure that out. At 10 seconds, it is at 10 meters. At 6 seconds, it is at 22 meters. And that looks like a negative 12 to me. Divided by 4 seconds is negative 3 meters per second. How do they compare? Well, this one's positive and this one's negative, and this one's a little bit bigger in magnitude than that one is. I don't know if I would have noticed that. Can I tell by looking at the graph how they should compare? I can. Okay, going from left to right for that first batch of data, it's going uphill. It's got a positive slope. For the second batch of data, it's got a negative slope. So the slope of that graph gives us the velocity of the particle, and it tells us the sign too. Can I write an equation of motion for the object? No, I can't, because it has two different average velocities depending on what I'm talking about. Now I can write two equations of motion for it. One that works for 0 to 5 seconds and one that works for 5 seconds to 10 seconds, but I can't write an equation, just one. So it's a more complicated situation in this case. I think the next problem that's in this group, yeah, this is one that I will save for tomorrow, but there's a one more problem that we can take on here. And it's this, a word problem, okay, which for a lot of people, what intimidates them most about physics is that every problem is a word problem. And so we need to understand the physics concepts, but then we also have to be able to convert situations like this and try and figure it out. We will have a fairly limited number of equations that we'll use. In fact, for this first week, this is pretty much the set of equations, but it'll be challenging. And that's the hard thing about physics. And it's something that eventually everybody who takes physics is going to reach points where they're struggling with the problems because the concepts get complicated. And maybe it'll be in your first quarter of it, maybe it'll be in your second or third, but it happens to everybody, and you get better at it. And the whole point of taking classes like this is that you improve your problem solving abilities. You may not ever get outside of this class and you may never solve a problem like this again, but the approach you take to solving the problems will help in other situations. So it trains your mind. All right. Anyway, this situation, we've got a car that moves to the right with a constant velocity of 22 meters per second. So if it's constant, that's also its average velocity, 22 meters per second. At some particular instant, and let that be when t is 0, the car is 5 meters to the right of a particular point, which we will use as the origin. Hey, if it's t0, then its position at that time is x sub 0. And so I can say that that's 5 meters. And use that information to write an equation of motion for the car. Well, here is our generic form. X is equal to x naught plus v average times t. I just have to plug in this for x naught, 5.0 meters. Plug in that for v average, and I'll wrap it in parentheses just to keep things a little bit tidy, times t. And then, what will be the position of the car at 7.5 seconds? Well, this is my equation that tells me where it is as a function of time. All I have to do is take that 7.5 seconds and plug it in there. So x is going to equal 5.0 meters per second plus 22 meters per second times 7.5 seconds. Then we'll see what we get here. 5 plus, whoops, helps to turn your calculator on first. And I get about 170 meters. So that's quite a ways. That's about 2 football field lengths in 7.5 seconds. So pretty good. 22 meters per second is somewhere between 45 and 50 miles an hour. So it's going at a pretty good clip. All right, a second car now enters the picture. At 2.1 seconds, this car is 4 meters to the left of the origin, moving to the right with a velocity of 31 meters per second. Determine the equation of motion for this one. This is kind of complicated. I need a blank piece of paper to sketch this out. So pick one that I've already written on. There went my calculator. Oh well. So I'm going to make an axis in this case. I probably don't need to have, well, maybe I do need some negative x values on this. We'll see. Oh yeah, I do, because it's to the left. So here is x in meters. Here's t in seconds, and I'm gonna, since I don't actually have divisions on here, I'll just do a sketch. But it says at 2.1 seconds, so this is my origin for both these things. 1, 2, 3, 4, 5, 6, or whatever. At 2.1 seconds, it's 4 meters to the left of the origin. So it's over here at that time. So that's where it is at 2.1 seconds. So this would be minus, or 2.1 seconds and minus 4.0 meters. And this one, it says, has a velocity of 31 meters per second. Oh, what's this going to look like? I wish I had graph paper. That would really help. But I guess I did -1, -2, -3, -4. This thing's going to have a really steep graph, and it's going to go like that somehow, but I don't know exactly what it's like. And I probably, I don't know, probably made it too steep. But I can do something with this. I can say for this second car, it's going to have an equation that looks like where it is at time 0 plus its average velocity times t. Now, I don't know where it is at time 0. It's somewhere to the left over here, but I do know its average velocity, and I know that at 2.1 seconds, it was at -4. So I can figure out the average or where it is at time 0. So at 2.1 seconds, x is -4.0 meters. So I'm going to plug that into here. I'll say -4.0 meters is going to equal wherever it is at time 0, which I don't know, but that'll be plus the average velocity, which was 31 meters per second, times 2.1 seconds. Okay, so this was a puzzle that I had to solve. I know that this equation describes what it's doing, and I happen to be given where it was at a particular time, and so I was able to plug those into there and figure out the equation. So x naught is going to equal -4.0 meters minus 2.1 seconds times 31 meters per second. Okay, I didn't make my graph look correct at all, but that's all right. Yeah, it's going to be way back there. -4 minus 2.1 times 31. Then I get minus 69 meters. Okay, well, now that I know that, I can write the equation of motion for this second car. X for it is going to be minus 69 meters plus that average velocity, 31 meters per second, times t. So there, I have the equation of motion for that second car. That was complicated. I wouldn't have expected you to be able to do that one right off the bat. Then it asks, determine when and where the second car overtakes the first. I should call this one X2 for the second car. The first car, I should call X1. And now that I know equations of motion for both of those things, let's see. X2 is equal to minus 69 meters plus 31 meters per second times t. By the way, I could make a graph of this. Let's see, that was the first one. Yeah, I could kind of make a sketch of what's going on with this situation. At way down here at minus 69, let's see, is where that one is at time 0. The other one is at 5 meters at that time. And this is not a good graph at all. If I had graph paper, I'd make it. But this one has a smaller average velocity. This one has a steeper average velocity. Missed. Close enough. Just make the dot bigger. Perfect. Okay. Anyway, the second car overtakes the first when their two lines cross. And so at that time, they'll both have the same x value. This is, remember, x on that axis. This is a chase problem, so I can figure that out. I just set these two times equal to each other, or these two x's equal to each other. Whoops, this is the x. Here's x1. And so I say x1 equals x2. So 5.0 meters plus 22 meters per second times t is equal to minus 69 meters plus 31 meters per second times t. And so this is a linear equation. It's not bad. I kick that across and I'll get 74 meters over here. Subtract 22 meters per second from each side. And I tend to do two algebra steps at once. Sorry about that. Maybe I'll convert it into two. 22 meters per second equals, I already got rid of the 69 over there. It'll be 31 meters per second times t. Subtract this from both sides, and I'll have 74 meters equals 31 meters per second times t minus 22 meters per second times t. Forgot that, is equal to 9 meters per second times t. And then I can solve for t. That's the when. And then where, I'll take this t that I figure out and plug it into either equation, and it should give me the same value from either one. Okay, I kind of rushed through that. You may want to watch that over again and think about it a little bit, and we'll start tomorrow by moving on from there. Be watching this afternoon. I'm going to put up a lab assignment for this week, which is basically to watch the videos on significant figures and do some unit conversion practice. And that'll be the assignment for this week. I'm not going to collect the unit conversion practice, but watch the videos on that and learn how to do it. And then for the lab assignment, there's the quiz that you'll take for that. And again, it's a 15-question quiz. If you know what you're doing, it takes less than 15 minutes to do it. In fact, it might take 5 minutes to do it if you know what you're doing, but or less. If you don't know what you're doing, you'll be flailing around and miss a lot of them, but you get 3 tries at it. So that'll be the lab assignment, and I'll post that later this afternoon. So any questions? I know I raced through that last problem on there pretty quick, but we can go on from there tomorrow.
Oh, I have like one question.
Okay.
So for when you're determining when the second car passes the first car, what you ended up doing here, could you bring the paper back?
Oh, sure. Let's see. Share the screen again. Yep.
All right. So what you did there is, so to determine where the one car overtakes the other, you solved for t, was it?
Yeah, because it said determine when and where the second overtakes the first. And this is a really rough sketch, but it's a sketch of, this is the graph of the first car's thing. This would be x in meters and t in seconds. And so there's what the first car is doing. The second car is traveling faster, but it starts from a long ways behind the first.
Yeah.
And so I've got an equation for x as a function of t for the two cars. And what I know is that where the second one overtakes the first is that they'll have the same x position. And so I just
Right.
set their two equations for x equal to each other.
All right. And so if you go back, so you flip the paper.
Yeah.
All right. And so by solving it, you find that it overtakes the second car at 74 meters at.
Well, I'd have to divide both of these by 9 meters per second, and then I'd get some time, actually. 74 divided by 9, and I get about 8.2 seconds. I should have written this problem better so I'd actually have two significant figures on this. I'm down to one, but it's at about 8 seconds. So.
And so then the car would overtake it at 8 seconds, basically.
Yeah.
Oh, yeah.
And then knowing that, I can plug it into this equation and find out where they are. That'll be the where part. But when I make a sketch of a graph like this, it gives me an idea of what's going on with the situation. Here's car 1 and here's car 2, and eventually car 2 is going to catch up with that other one. But it takes a while anyway. Any other questions on that? I know it went kind of quick, but it'll be recorded so you can watch it again if you need to.
I had a question. So on the previous page, we didn't, you didn't write an equation out. Can you explain how come we didn't, why we couldn't make an equation for, I think it's on the back.
Oh, was it the one where we had the V?
Yeah.
Yep. Because I couldn't write an equation of motion. It's just a yes/no question, actually. The F is. And the reason we can't is because it's got one average velocity for this part, but a different average velocity for that part. And so I can't write one equation that describes both of those situations. It would.
Okay.
And so, and that's all. This is sort of like a trick question in a way. And the answer to it is no, you can't, because there's not a nice way to write an equation for a V like that.
All right, thank you.
Uh-huh. All righty. Well,
I have like one last question, kind of a weird one, kind of quick. But so X naught is displacement at 0, I think. I'm not saying that right.
It's the position at 0 seconds.
All right.
The position when the t is equal to 0. And pretty soon, in fact, starting tomorrow, we're going to start dealing with something called acceleration. And that's the problem that we didn't do today. But we'll start with that tomorrow. And in acceleration, something that we'll think about is what's the velocity when t is equal to 0. So we'll call that v sub 0 or v naught. And that's as complicated as we'll get in equations. So yeah, but we use, it's a common thing to use a subscript of a 0 on something and call that, you know, x naught or v naught. Actually, in reading about the coronavirus, there's a number that they call R naught, and R naught is a measure of, in this case, it doesn't have anything to do at time 0, but it's a measure of the average number of people that an infected person spreads the disease to. And if we get R naught under 1, then the number of infections will fall over time. And if we keep it under 1, it'll get down close to 0 eventually. But as long as R naught is greater than 1, then the number of infections will continue to increase. So in Washington State for a while, we had our R naught value was less than 1, and now it's back bigger than 1 again. We kind of bounced. People have gotten careless. So anyway, that's that. That's not physics, that's epidemiology, which is sort of outside the scope of the course, but it is a number with the same subscript and stuff we're doing. Well, I'll turn you loose and see you again tomorrow. You should be checking out things in chapter 2 of the book. Let's see. We're in the introductory sections of chapter 2, but we're actually going to be moving into section, oh, what is that section? Wow, section 2.4 tomorrow. And we might get into 2.5. They have lots of example problems in the book, by the way, which are helpful, and they go through them in quite a bit of detail. So,
how much of the book should you be reading within relation of lectures?
I'll try to give you a section. Chapter 1 was just kind of introductory material, but they had stuff about units and precision and sig figs and a little bit of historical background. And so far, yesterday we talked about displacement. So that was section 2.1. I skipped section 2.2 for now. And then today we were doing 2.3. And tomorrow we'll look at 2.4 and 2.5. It's a good idea to read them before class. But don't read them, don't kill yourself trying to understand everything in depth. Just read them for some familiarity with the terms ahead of time. And then when you want to read it carefully is when you get a homework assignment and you want to go back and look and see, did they do any problems like that? And then you can do a careful reading and check out their examples and things like that. So, but repetition is good. Do a first quick over reading just to familiarize yourself, and then go to class, see problems done from that area, and then you can go back and do a more careful reading. And that's something that, boy, I can remember taking classes and probably going through 3 or 4 readings of certain textbook parts to try and understand them, because they got complicated after a while. Anyway, I'll turn you loose. Go have lunch, something like that. And I'll get that stuff posted up there later today. I think my video may have actually finished rendering here today. Nope, it's still going. But in a while, I'll be able to get it posted on the class site. Okie doke.